Okay, so far we've looked at the relationships between pressure and volume, volume and temperature, and pressure and temperature in Boyle's law, Charles' law, Gay-Lussac, or Amonton's law. So if we represent these three, we can see that pressure was inversely proportional to volume. So pressure is proportional to 1 over V. If we rearrange this, we can get pressure times volume is always equal to a constant, and this was Boyle's law. We've also seen that volume is proportional to temperature. If we rearrange that, divide both sides by temperature, volume over temperature is always equal to a constant. And if we get, that was Charles' law, and we've seen that pressure is proportional to temperature. So if we divide both sides by temperature, we get pressure over temperature is always equal to a constant, and this was Gay-Lussac's or Amonton's law. So we have three relationships here. Now if we're to combine those three relationships, we come out with pressure times volume from our first one, divided by temperature from both of these two, is always equal to a constant if we hold the mass constant in a gas. Now this is known as the combined gas law because it brings together three different laws. So we can use this to predict changes. So if we adapt this equation, this is always, PV over T is always a constant, so we can have an initial set of conditions where we have a pressure, a volume and a temperature. If we adjust those three, we can have a final pressure, volume and temperature. And we can use this particular equation, which is our combined gas law, to predict an unknown. So let's have a look at how we might do this. Let's say we have a problem such as this one. We have a balloon with an initial volume of 3.65 litres. And that's sitting at the base of a mountain, and it experiences a pressure of 755 milligrams of mercury at 29 degrees Celsius. The balloon is taken up the mountain where the final temperature at the top of the mountain is 18 degrees Celsius, and the balloon experiences a pressure of 687 millimeters of mercury. So we want to know what the new volume of this balloon would be once we've taken it up that mountain. The way that I approach all these problems is to underline those things that are important to us. So the initial volume, 3.65 litres, so we'll write that down, 3.65 litres. We'll also write down our initial pressure of 755 milligrams of mercury. And we also know that the initial temperature is 29 degrees Celsius. So we write down our T1 as 29 degrees C. Now we must convert this to Kelvin for this equation to work. So 29 plus 273 gives us 302 Kelvin. Now we're also told in the question that the final conditions, we have 18 degrees Celsius, our T2. Once again, we've got to convert that to Kelvin, so we add 273, so we get 291 Kelvin. And the last piece of information that we're given is the final pressure of 687 millimeters of mercury. So if we look through here, we try and find a formula that involves our unknown, our V2. So we have our combined gas law in that form, P1 V1 over T1 equals P2 V2 over T2. And then the object is to isolate V2. So to do this, we first of all need to multiply both sides by T2 to eliminate T2 from this side. And then secondly, we need to divide both sides by P2 so that all we're left with is our V2. And if we do that, we get V2 equals P1 V1 T2 over T1 P2. So that isolates the term that we want to find. And now, once we've converted our temperatures, we put in our numbers. So we've got our P1 is 755 milligrams of mercury times our initial volume of 3.65 litres times our final temperature of 291 K over our initial, or T1, our initial temperature of 302 K times our final pressure of 687 millimeters of mercury. And if we do this calculation, we look at our units. So we've got millimeters of mercury there and there. we've got our measurement for temperature there and there. We end up with our final units of litres, which is what we want, and we get the number 3.87. So in other words, we go from the bottom of the mountain to the top of the mountain, and our volume changes from 3.65 litres to 3.87. Does this number make sense? Well, we're going from higher pressure to lower pressure, so we're getting a reduction in pressure, so our volume should increase. And we're also going from a higher temperature to a lower temperature, so our volume should decrease. But the balance between the two are in favour of a slight increase in that volume.